Okay, so I've got a few questions to do. The lecturing example that I didn't finish, and question 2C from the practice test. I'm going to split these into two videos. Let's look at the example I was doing in lectures but didn't finish. So we're given a probability density function for the lifetime of some electrical device. It's here. We're asked to find the cumulative density function. We're asked to find the probability that a single device lasts longer than some time period. And we're asked what's the probability that of 6 such devices, at least 3 will function for at least 15 hours, right? 15 time units. We're also going to calculate the mean and variance of this distribution. And we're also going to check that this distribution is indeed a distribution. That is, that this thing integrates to 1. And we'll also draw a picture of the probability density function x, of x. Right, so let's get started with those tasks. So we've got a PDF. Now, the equality symbol here doesn't actually matter, right? Because it's a continuous distribution. X greater than 10 is equal to the probability of x greater than or equal to 10 because equality contributes nothing. It's an integral under a PDF. Just noticing my So this is a lecture example I didn't finish. We've got this probability distribution here. We're going to check that it is actually a distribution, that is, that it integrates to 1. We're then going to plot this distribution, find the CDF and plot it, calculate the mean and variance, think about them for a bit, and then we're going to answer some other questions to do with this probability that are up here. Okay, so let's check that this thing's a distribution. No, it's still lagging. Fuck me dead. Why haven't you fucking closed? Piece of shit. Okay, so this is a lecture example I didn't finish. We're going to crack on and do this question, and we're going to do some extra bits as well. Excuse me. We're given the probability distribution. like this. Let's check that it is indeed a distribution by integrating it. You know, of course, that this should be true. And when we sub in, we get 10 as our bottom limit, because x, if we're less than 10, it's just 0. So there's no real interest in that end of the distribution. You can do a piecewise integration, like you can take this whole thing and put it in there, but you'll just find you're integrating 0. So we want to check this. This is equal to add 1 to the power, divide by the new power for this integration. Because it's one of these unusual integrals with infinity in the limit, we have to take a little bit of care and interpret that as a limit as x tends to infinity. Now, it's going to be minus 10 over the bottom limit, which is 10. Now, the limit as x tends to 0 of, the limit as x tends to infinity of 1 over x is just 0, so this is 10 over 10, or 1. So indeed, this is actually a distribution. That's nice. Oh no. What does this distribution look like? Let's draw the PDF as a function of x. At x equals 10, we suddenly jump from 0 up to 10 over 100. That's 1 over 10. And then we start decaying like a 1 on x squared decay. So our distribution, our PDF, looks like this. Let's now find and sketch the CDF, which is just the indefinite integral of the PDF. So I'm going to write the indefinite integral fairly carefully, noting that we can change the variables inside the integral. It's just a dummy variable, and we've got our x in the top limit now. So when we integrate from negative infinity up to x equals 10, all right, under this definition, we're going to be integrating 0, so it doesn't matter. We may as well start with a bottom limit of 10, and this is our function. Again, we add 1 to the power, divide by the new power, and substitute in the limits. When we do that, we find this for our cumulative distribution. Now, we've got to remember that this is for x greater than or equal to 10, and it's 0 below that, right? Because here, right, we've actually put a condition on this here. So our CDF looks like this. We've got 0 when we hit 10. We're going to asymptote to 1. As x gets very, very large, this term's going to get small, right? So we know that we're going to have an asymptote to 1. What does 1 over x look like? Well, 1 over x looks like something like this. So if we subtract it from something, right, we're going to get a graph that kind of looks like this shape, right? Upside down. So this curve kind of represented, but flipped over. So if we take x equal to 10, well, we get 1 minus 1, which is 0, right? And we know that we grow in this decaying 1 over x type fashion. So that difference is going to get smaller over as x gets bigger. It's going to look something like this. Right, so that's a plot of the CDF and how to construct it. The expectation of x is given by this integral, which essentially works out a center of mass of the distribution, right? So you're looking for the center of mass of this thing here, right? Where's your most mass? But it relies on the fact that the integral converges, right? This thing has to decay quite quickly for the expectation to actually be defined. Let's see what happens in this case. We substitute in below x equals 10, we're going to get 0, right? Because we've got no probabilities of ever occurring there. So that's what we get for x greater than or equal to 10. As we proceed, we add 1 to the power divided by the new power. Oops, no we don't. We note that this cancels, and so we're integrating 1 over x, and so this is a logarithm now. Unfortunately, the logarithm is undefined at infinity. So this limit, as x tends to infinity, of the log of x is undefined. So we're done. We cannot define an expectation. This can happen. Just because we define something doesn't mean, we define an expectation doesn't mean we can calculate it for every distribution. And this distribution does not have an expectation. We have to come up with some other measure of center for it, which we won't discuss here. Just know that the expectation is undefined. If we then consider the variance is, you can consider it to be this, for example. The expectation of the square differences of the observations or the random variable from the expectation. So if you can't define an expectation, right, you can't calculate this. If the expectation is undefined, then the variance is also undefined. Not true the other way, I guess. I assume that. I wonder if there is a pathological case where the variance is undefined and the expectation is defined. It seems feasible. I don't have an example off the top of my head. But it's something to think about, I guess. The next thing that we're asked in the question is to calculate the probability that the random variable x takes a value greater than or equal to 15. There's a few different ways to do this. You can use complementary probabilities to rearrange this to be x less than 15. But it's actually very straightforward to calculate straight from the definition of our probability distribution. So if we go back and plot our PDF again, we find this, where after the area under the curve from 15 upwards. All we have to do is integrate, and that's actually so straightforward in this case. That's what we're going to do. Because 15 is greater than 10, I'm not even going to worry about the distribution down here. It doesn't come into it. That's the integral we have to compute. Add 1 to the power, divide by the new power. Now we've got to interpret the top limit like this. And then the bottom limit, obviously it's a negative quantity, subtracting off a negative quantity, we've got 10 over 15. So this top part, as x tends to infinity, this top part disappears, it goes to 0, and we're left with 10 over 15, which is 2/3. The final part of the question asks us, if there are 6 of these items, what's the probability that at least 3 function for 15 time units? Function for at least. At least 3, yep. At least 15 hours. So let y the event 1 device, or sorry, let y be the event devices in this 6 function for 15 hours at least. So I guess instead of saying the event, we should say the number of devices. And so we're after the probability that y is greater than or equal to 3. All right, so we want at least 3 of these things. This variable, y, will be distributed binomially. N is equal to 6, and the probability is greater than 15 time units. We've already worked this out. That's this probability up here. Px, a single unit, functions for this long. So that probability is 2/3. What we've assumed here is that these devices are all independent. They have an independent probability of lasting this 15 time unit condition. So these become these individual x variables become part of our Bernoulli trial, which we then construct into a binomial expression for the 6 of them. And we want the probability that y is at least 3. So that means we're after the probability y greater than or equal to 3 is equal to 1 minus the probability that y is less than 3, which is equal to 1 minus the probability that y is equal to none, plus that. And now you just use the binomial formula, which is on the formula sheet. We got 6 choose 3, 6 choose none, sorry. The probability of success was 2/3 to the 0. Probability of failing is the complement of that. All 3 of them have to last less time. 6 choose 1, 2 over 3 to the power of 1. 1/3 to the power of 2. And then finally 6 choose 2, 2/3 to the power of 2. And then 1/3 to the power of 1. Right. And that thing will evaluate some number. That number is apparently 0.899. About 90%.